All right, so I'm recording that now. So what we're going to be doing today is we're going to be taking, for those of you guys who are in here, we're going to be taking a look at a very brief introduction to BGP route reflectors and confederations. So I figure in order to begin talking about what we're doing for the demonstration today, I figure we might as well talk about the problem that BGP RRs and confederations solve in case you're unaware of it, which is going to be Ibtp related. So what we're going to do is we're going to go ahead and just draw a basic diagram here. Let's call this 4 routers here. We can put them in a little ring. R1, R2, R3, R4. And we're just going to draw a little ring here. And what you'll sometimes hear this referred to as is the Ibtp full mesh problem, or what you'll sometimes also hear it called the split horizon rule. And so the problem is simple. Let's say we have a network off here, right? We'll call this 1111/32. So we'll say this is a loopback interface, and then we're advertising this out into the topology. So we're using Ibtp, BGP, AS. I'll use a different color here. BGP, AS 100. So we're using BGP AS 100 there, and then we're doing IBGP between all these routers here. So R1 is paired with R2, R2 is paired with R4, R4 is paired with R3. You get the point. So these guys are paired in a sort of ring. And so what you might think happens, and what would happen if this were all eBGP relationships, is that R1 is going to push this network into BGP. It's going to use a network statement. It's going to inject into BGP. And R1 advertises it to R2, R2 advertises to R4, R4 advertises to R3, and in a perfect world that would stop, but you might also get an advertisement back around, right? Now, in a situation like this, how do we stop loops, right? How do we stop this routing update from looping around and potentially creating a routing looping a data plane? Well, the solution that eBGP uses is the AS path attribute. So when you're doing external BGP and you are peering between ASes, what happens is when R1, before it sends out this update, it's going to modify the AS path attribute. And where the AS path attribute is normally blank, it's going to prepend rather its own AS to it. So let's say it's 1 here, right? So it prepends its own AS, then it advertises it. When R2 gets it, he's going to see that AS, and he's going to do a loop prevention check. And the loop prevention check is really simple. It's going to check the AS path, and it's going to ask itself, is my AS in here? Now let's hypothetically say for this particular question here that 2 is in BGP AS 2, right? So these guys are all eBGP, so they're in ASes, and let's say that their AS number is their router number. So they're going to look at the AS path, and 2 is going to say, oh, well, my AS number 2 is not in here. So it's going to accept the update, and then prior to sending it to R4, it's going to prepend its own AS path, or its own AS to the AS path, which means that the new AS path coming out of R2 is going to be 2, 1. And that's its way of marking that it has received the route and that it's passed through the AS. So when it exports it out of AS2 to router 4, which is an AS4, it's going to prepend it, and then it's going to advertise it. R4 does the exact same thing. Before it exports it to R3, it's going to go 4, 2, 1. It's going to export it here to R3. R3 is going to see that the update is 4, 2, 1. It's going to, prior to re-exporting it to R1, it's going to prepend its own AS, 3, 4, 2, 1. So that's the order there. Now, hypothetically in this scenario, I'm saying that R1 didn't try to advertise it back out to R3, because you might say, okay, well, if these guys are peered, then R1's going to advertising out to both R2 and R3 when it first does the initial advertisement here of this network. We can hypothetically say that there's a route map outbound applied to this peering that's blocking that network, right? The point is, it's flowing in this direction. It's going to eventually come back to hit R1 in the face. And when it hits R1 in the face, the AS path is going to be this. And even if that does happen, if you'll notice, the AS is there. So R1 with its AS1 is going to look in that AS path. It's going to say, oh, well, this AS is here. So clearly that means that the route has flowed through my AS already. And so this has to be some sort of routing loop somewhere out there on the internet. So it's going to drop the route. It's not going to accept it. And so that's how we kill loops in eBGP. The problem in iBGP is that you can't do this because an iBGP update, when it goes out, it doesn't prepend the AS path. So because these guys are all in the same AS. So if it did append the AS path, or prepend rather, I don't know why I keep saying append. If it were to, I'll just rewrite AS path down here. So if it were to prepend it on export, R1 would prepend 100. So now we're assuming that this is all iBGP and that this is all in BGP AS 100. It's going to prepend the update with AS 100. It's going to flow over to R2. And then R2 at that point sees its own AS in the AS path and just immediately drops it. So iBGP as an operational principle just cannot, there's no way that checking the AS path for its own AS would work because everyone is in the same AS. And so you wouldn't be able to get the route out because that next router would immediately drop it because it's a presumed loop. So AS path prepending in just regular iBGP doesn't work. So you need a better solution than that. And so the designers of BGP just basically said, okay, I hear what you're saying. I hear that there's a problem here. Here's what we're going to do. We're going to implement something called the split horizon rule. And the split horizon rule just says when R1 sends this update out, so it's going to send it out to R2, it's not going to prepend the AS path, which means that R2 is going to accept it. And BGP just says, okay, we'll just implement a rule that if you receive an update from a iBGP neighbor, you don't advertise it to other iBGP neighbors. So you can advertise it to an eBGP neighbor, right? If we had like an R5 here and we had this connected and this is eBGP, then sure, right? We could advertise it out here, but we can't advertise it out here because that could be a presumed loop. So that was the solution. That's the split horizon rule. If you receive a route from an iBGP speaker, you can't re-advertise it to another iBGP speaker. And it works, right? It works to stop loops because if you can't re-advertise, then you can't form a loop. And that was their solution for it. Now, the problem with that is that if R1 advertises 111 out to R2, and let's say we remove the route map that was blocking it outbound from R1 to R3, and it's allowed to advertise this network out to R3 there, theoretically that's fine, but let's say we had some network off of R4, some PC here that wanted to reach this 1111 prefix. Well, R4 can't because R1 may have advertised it to R2 and R3 there, but the problem is that this is not full meshed, and Split Horizon is going to say, okay, R2, you can't advertise this back out to R4, and R3, you can't advertise this out to R4. So R4 is entirely in the dark in terms of what this route is here, and so anything that's connected to R4 is not going to be able to reach this network here. It's off of R1. Only R1, R2, and R3 have knowledge of where that network is, which is a problem because ideally you want this router also to be able to reach it. And so there's three solutions to this problem. There is just full meshing it. There's a thing called route reflectors, and there's a thing called confederations. So the latter two are part of the discussion today, but there is the manual nitty-gritty method to solve this, which is, well, if you can only advertise a network out of a directly a direct peering, as in you can't do multi-hop peerings, or not multi-hop, I should rephrase that, as in you can't advertise an iBGP route across multiple peerings there, then the solution is that you just form multiple peerings. So you say, okay, well, we're going to make a full mesh of peerings here. So R1 peers with R2, R3, and R4. R3 forms pairing with R1, R4, and R2. And then, yep, so this should be full mesh here. So in a full mesh here, everybody has a connection, has a peering with everyone else. And this means that no matter which router here is going to be advertising a route, it's going to always go out a direct peering here instead of having to traverse multiple routers and break the split horizon rule. And so that works, right? But the problem is that this is very intensive from a configuration, from a control plane, and from a data plane perspective. Because the full mesh here, if we're doing full meshes, that's going to comply with our full mesh rule, which is n times n minus 1 over 2, where n is the number of routers. So that's our full mesh equation. And I shouldn't say routers, actually, I should say devices, because this is a more general equation. So basically, if we have 4 routers, it's 4 times 4 minus 1, which is 3 divided by 2, so that's 6. And if we're counting peerings here, 1, 2, 3, 4, 5, 6, we know so you have 6 peerings. But imagine if you had, say, 100 devices, that's 100 times 99, which is 9900 divided by 2. That's 4,000 peerings you're maintaining, which is a big problem from a configuration perspective, because who wants to sit down and configure 4,000 peerings? That's a big problem from a control plane perspective, because those routers have to maintain 4,000 peerings from a control plane perspective, so it has to do keep alive and all of that, and it's wreaks havoc from a data plane perspective, because every single time this router wants to push an update out, it has to push 4,000 updates, one to every single peer, instead of letting the update just traverse and hop off of intermediary routers. And so full meshes are just a problem all around, because they don't scale well at all, no matter how you look at it, right? It's convenient, it's simple, relatively speaking, because you don't have to involve any other techniques, but it's extremely cumbersome and it just doesn't scale well at all. And so the designers of BGP and a lot of other smart people quickly realized that this was a really big problem. And so they designed, gonna just redraw AS path here. I don't know why I'm doing that, just I am. So the designers of BGP saw this as a problem, and so addressed it with 2 other techniques I also mentioned, route reflectors and confederations. Route reflectors are the simpler of the 2, and confederations are the more complicated, or is the more complicated of the 2. So they both take 2 different techniques to helping you get around this kind of problem. So an RR is going to help you get around the problem by just outright breaking the rule, right? It's breaking the rule because it has extra safeties in place in order to make sure that that you don't run into loops. Now, a confederation, on the other hand, is going to help you get around it by sort of sneaking around it. So it's not going to break the rule, but it's going to sneak around the restrictions. And I'll describe what I mean by that in a second. So hopefully you guys know that the loop prevention BGP is done by the AS path, so I'm going to erase that so I get more space. So when we do a BGP route reflector, basically what we're doing is, let's say we make this router here, I'm going to go ahead and highlight it with a little asterisk. So let's say we make that router a route reflector. What we're doing when we make that router a route reflector is we are saying that, okay, you and only you have permission to reflect the routes, meaning that when they come in, you are allowed to advertise them to other IBGP speakers. You're allowed to directly break the split horizon rule, where the split horizon rule is saying that, again, if you get an IBGP update from an IBGP speaker, that you are not allowed to advertise that update to other speakers. Now we're saying, okay, Reflector, you are the only person that's allowed to do that. You are the only person allowed to break that rule. Everyone else is still following it. These, what we call route reflector clients, are still following that rule, but you aren't. Now, what this means is that we can redesign the topology a little bit. We can go ahead and scratch out these peerings and then just form a peering straight to route reflector. And so what we're doing is we're forming an effective hub and spoke, right? Now you can keep this if you want, but ideally we'd have a peering to the route reflector. So this creates a logical hub and spoke where we have the route reflector as the hub and then every single client as the spokes there, where updates that go up to the reflector can come down to the rest of the clients and even non-clients. We'll discuss some of the rules for reflection in a moment. So that seems fun, but the question that might come up is, okay, well, the reason that we didn't allow, the reason that we have split horizon in the first place is because we were concerned about loops happening, is because we were concerned about the possibility of a data plane loop. So how would route reflectors get around this? And if they're directly breaking the rule, then that kind of circumvents the entire purpose of having the split horizon rule in the first place, which is loop prevention. And so the designers of route reflectors thought of this, and so they baked into the standards 2 additional path attributes that are designed to take the place of the AS path for loop prevention. So when we're talking about Ibtp, we're talking about route reflectors. There are 2 ways you can do loop prevention. There's the cluster ID, and then there's the originator ID. So when we're talking about the cluster ID, this is basically a new version of the AS path, right? So we have to have something that serves in the role of the AS path if we're not prepending the AS here. And the cluster ID is that thing. So the cluster ID is a list of route reflector cluster IDs. And what a cluster ID is, well, first you have to define what a cluster is. A cluster is when we talk about a route reflector, right? And we talk about have all of its clients. This logical administrative boundary is a cluster. It's a route reflector cluster. So a route reflector cluster, strictly speaking, is a route reflector, and all of the clients that it services, all of that is wrapped up and together form a cluster. And that cluster has an ID. Now, it's a 32-bit dotted decimal number, like an IP address, except the difference is that the BGP router ID has to follow the IP address standards, so it can't have an invalid IP address as the BGP router ID. The cluster ID doesn't follow that same rule. So as long as it's a valid 32-bit dotted decimal number, even if it wouldn't be a valid IP address, something like 0001 would not work as a BGP router ID, but it works as a BGP cluster ID. So the cluster is identified by a 32-bit 4-octet dotted decimal number, just like an IP address. And this cluster ID is by default the router ID of the route reflector. So you can change it or you cannot change it. It's up to you, right? In most situations, you shouldn't have to change the cluster ID because ideally you would have unique router IDs across the domain, and so you would also have unique cluster IDs across the domain. And the unique cluster ID part is important because just like how you can run afoul of the eBGP loop prevention rule by, say, having a router here, right, where this is an AS1, this is an AS2, and this is an AS1. Even if this is not a loop, if this is eBGP and we're just advertising things like this, rather this R3 here is going to think that an update coming from R1 is a loop because the one is in the AS path, even though it's really not. And it's all because the ASes here are unique. So just like that can happen with ASes, that can happen with clusters as well. So if your clusters aren't unique and you have multiple route reflectors, and you somehow get a route reflected to another cluster, even if it would not technically be a loop, because the route reflectors see their own cluster ID, they're not going to accept it. And that ties into how the cluster ID helps with loop prevention. So every time the route reflector reflects a route, so let's say we have that same 1111 network that's coming in from R1 to R2. When R2 gets it, it's going to go ahead and prepend its route reflector cluster ID to that cluster ID attribute, it's going to add the originator ID, which is what the route reflector received the route from. So it would be the router ID of R1 here. It's going to go ahead and take that, put in the originator ID, and then it's going to reflect it out. So it's going to, it'll even reflect it back out here. It'll reflect it out to all eBGP, or it's going to advertise it to all eBGP peers because it's not considered a reflection if it's an eBGP peer. So it's going to advertise it to all eBGP peers. It's going to advertise it to, or it's going to reflect it to all clients, and it's going to reflect it to all non-clients. So in that case, that means that when R1 sends the update for 1111 to R2, it's going to reflect it out to R3, reflect it out to R4, and it's even going to reflect it back to R1. Now, you might be saying, okay, well, this is a clear loop, right? Because R1's advertising it to R2, and R2 should straight back advertising it to R1, right? So how is that not a loop? Well, this originator ID is the key. Because these routers here, these clients, don't actually care about the cluster ID. The cluster ID is meant for route reflectors to be able to check whether there's a loop. These regular clients and non-clients, non-route reflectors do not care about the cluster ID. So the way that this works is that R1 sees the, what's it called? It sees the originator ID, and it sees its own router ID in there because R2 put the router it received the update from, which is R1's router ID, into the originator ID, and then reflected it. So when R1 gets the looped reflection, it's going to see its own originator ID, and it's going to drop it right there for the same reason as if it sees its own AS in the AS path. Because it sees its own originator ID, it knows that it was the one who originated the update in the first place, detects a loop and drops it. And these are all optional non-transitive attributes. They are non-transitive and they are removed by any edge-facing peer when they exit the AS. So if this router has to advertise a reflected update to an eBGP peer, for example, it's going to drop the cluster ID or drop the cluster list and drop the originator ID from the update, and then it'll send it out. So does anyone have any questions so far about what I've talked about with RRs? Second call. Yeah. So okay. A client, yep. It would still reflect it. Yep. Yep. So client IBGP, if you receive it from a client, you reflect it to everybody. The only case where the route reflector won't advertise it to everybody is if it comes from a non-client. So if it comes from a non-client, it will reflect it to clients, but it won't reflect it to a non-client. So you can't have non-client to non-client, but you can have non-client to client. Okay, yeah, I made them on that in a moment, but if no one else has any questions about reflectors, I'll move on to a quick overview of confederations, and then I'll do some configuration. Alrighty, no questions? So I'm going to go ahead and create a new layer here, and I'm going to hide these two. So let's go ahead and we're going to have to do a bigger scale example for this one to make sense, because confederations are really only used when you have a large scale environment. So if you have a moderate scale environment, you just didn't want to do full meshes, I have enough room there. So again, if you had a moderate scale environment that only had a few routers and you just didn't want to do a full mesh there, you can use a route reflector. But the problem is that route reflection is a very control plane heavy thing, right? Because if you think about it, you're placing yourself in the control plane path. You may not be placing yourself in the data plane path. That's going to depend on your IHP reachability and what you're advertising as next hop there, and any routing policy on the route reflector. So it can be in the data path, but if you're smart about your route reflector design, it's not in the data path, it's just in the control plane. But still, if you think about it, if you're receiving all of the updates, you are the choke point there as the route reflector. If you're receiving all the updates from all of the clients, all of the non-clients there, and you're reflecting stuff all around, That's a very control plane heavy task. And you often, if you have larger environments, if you say have like 10,000 clients, that doesn't work. And so you need to be able to have some extra scalability, right? And that's where confederations come in. And confederations, like I said earlier, they sneak around the split horizon rule by basically simulating eBGP within your AS. So if we have 8 routers here, let's say, so we're going to duplicate the topology we had before, R7 and R8. And then we go ahead and we do some orange highlights around here. And then we'll go ahead and do a larger yellow bubble right here. So we'll call this all BGP AS100. And then when we look at our confederations, what we're going to say, right, is that as far as this confederation goes, we have some sub-ASes. So this is going to be sub-AS, I'm going to call it SAS, sub-AS 65,001. I'll say why I'm using the private AS space in a second. And then we're going to say SAS 65,002. So I'm using this private address space here, or private AS space, I'm sorry, private AS space, because that's the recommended deployment there for your confederations. And the reason is that if you're using real AS numbers here, right, it can't be the same as this AS number down here, right? So let's say you use real AS numbers. So say you say 101, 102. If you have AS 101 or AS 102 out here somewhere, and their originating updates that come into your topology, if AS 101 is advertising a route that comes into this confed sub AS, it's going to drop it because it sees it as a loop. Same thing here. If it's 102 comes in here, it's going to drop it because it sees it as a loop, because it sees its own AS number in the AS path. So that doesn't work. So ideally, you'd be doing your sub ASs there as private ASs so that you don't run into any risk at all of having AS paths come in that have your AS number in it, your sub AS number, and then have to drop because of a loop, right? So that's kind of important. And then, though, that being said, nothing is forcing you from or nothing is forcing you to use private ASs. You can use whatever AS number you want there. It's just common design practice to do private ASs so that you don't run into any foul AS paths there. Anyway, so when we're talking about the sub ASs, the discussion there is going to be minimizing the scope of the full mesh requirement. So this doesn't kill the full mesh requirement entirely like route reflectors did, but it minimizes the scope that you need to do that. Because instead of having to, if these were all just an AS100 without confederations, each of these 8 devices would have to have full mesh pairings of each other, which means that full mesh equation time, 8 times 7 is 56, divided by 2 is 28. That means that we need 28 peerings here in total. That would be 28 lines to draw, and I'm too lazy to do it. But here, we only need to have full meshes within each individual sub-AS. So you can think of this kind of, for now, like these were just 2 separate ASs, right? Like if 65,001 were a separate regular AS and 65,002 were a separate regular AS, right? The only scope that the full mesh requirement applies here is going to be within 65,001 within these 4 routers, and within 65,002 with these 4 routers. And so that means that your full mesh requirement goes from 28 to 4 times 3 divided by 2 times 2, which is 12. So instead of needing 28 peerings, you only need 12 peerings. And that's if you're doing full mesh. Within these individual sub-ASs, you can have route reflectors. And that breaks it down even further. So if you want to do a full mesh, you'd be doing something like this, right? So you'd be doing 6 peerings right there and 6 peerings right there. That's a far cry from the 28 that you had to do. That's more than half reduced, right? So it's less than half of the pairings that you needed. I'm sorry. And then when you're going between sub-ASes, this acts like eBGP. So you are going to only need this one pairing, right? You can also have this pairing down here, but at minimum, you need this pairing up here to go between your sub-ASes. And so this acts like eBGP, which is why we have two names for these peerings right here. So if you're peering to other routers within your confederation sub-AS, we call it confed IBGP. So this isn't an IBGP peering, it's a confed IBGP peering. And this is not eBGP peering, it's a confed eBGP peering. Might be asking what's the difference. Well, when we get into confederations, we're not messing around with new path attributes. We're not doing any kind of originality or clusterless. We are doing just straight up AS path manipulation on these confed eBGP peerings. So this is still realistically iBGP, but it's going to prepend the AS path. So let's say we have the same update that's coming out from R1. Let's call this 1111/32. So when R1 is going to go ahead and advertise this out to all of its neighbors, R3 is going to take this and it's going to apply the split horizon rule within the sub-AS. So it's not going to advertise it down to the R4 peering that it has. Same thing for any of these guys. It's going to stop right there. But it is going to advertise it out to R5 because there's an eBGP-like peering there. So it's going to advertise it out to R5. And it's going to prepend the AS path. So if we look at the AS path up here, so this is the AS path of that update. And the AS path is blank, right? Because this is eBGP. So when R3 receives it, the AS path is blank. But when it does a confederation export, it's going to prepend an AS confederation sequence, which is surrounded by square brackets, if I remember correctly. So it's surrounded by square brackets, and it's going to prepend its confederation sub-AS number to it. And then that's what gets exported off. So if you had some kind of a loop within the confederation, this is how you identify it. If for whatever reason R8 had a peering here to R4 and it kicked it back around, this is what would get used in order to drop that. R4 would look at the AS path. It would say, okay, well, this is my own sub-AS number, so I'm going to go ahead and drop that. So it's the same tricks that eBGP uses to do the loop prevention, but now you're doing it with an iBGP because now you have separate sub-AS numbers, and so you don't have to worry about the other IBGP router dropping your update because it has own AS numbers. These guys have different sub-AS numbers, even if they're part of the same real AS100. And so as far as this goes, it's not much different than just regular eBGP goes, except, right, the difference is how this is treated, right? There's several differences. The first difference is how this is treated. So you'll know that step 4 of the BGP best path selection process is going to be the AS path length, right? And in the AS path length, it's going to go ahead and say, okay, well, how long is the AS path? And it's going to find the shortest one, and the shortest one is by fewest AS numbers. Now, if you've done BGP summarization before, you'll know that if you don't do atomic aggregate, you're going to have an AS set in there. And the AS set is going to tell you in an unordered list of the ASs that were in all of the summarized updates. Now, you'll know that the AS set, if you've done summarization, is counted by the BGP best path selection process as one AS. When it gets to step 4 there, it has to compare the AS path length. And so the value there is loop prevention. Well, in this case, you have AS confederation sets because you can do summarization within these confederations. And so you have confederation sets, and then you have confederation sequences like what we see here. AS confederation sequences and confederation sets are both counted the exact same way by the BGP best path selection process. and it's counted as 0. So when we talk about the AS path length there, it's all counted as 0, which means that even if you had one update that had one confederation sub AS and another update that had 7 of them, at the end of the day, they are treated equally, and both of them have an AS path length of 0, even though they have wildly different sub AS number counts there. And another thing, there's going to be how this update is advertised. If you recall from your eBGP studies, your regular eBGP studies, eBGP has certain traits when it advertises the update out. Like for example, it'll strip away all of the IBGP or non-transitive attributes. It will strip away. It'll change the next hop to the transport address. It will change the what's it called? It will prepend the AS path. It'll change the AS path attribute. Well, list is emulated eBGP. If it's within the same real AS, but it's different confederations, this is confed eBGP, and so it's going to be emulated eBGP in the sense that it doesn't follow all the rules of eBGP. So true eBGP peers change the next hop to the transport address in the update, as I mentioned. This doesn't. So if you're doing confed eBGP and you advertise this over here, the next hop that R1 put on is still the next hop that R1 put on, even as R5 receives it, because R3 doesn't manually change it itself. There it leaves the next hop alone. And also, local preference and multi-exit discriminators and all that are fully transitive throughout these sub-ASs, even if they're not in true eBGP updates. And so that's that, right? Any questions there? I think that's all I need to cover in terms of theory there. Yes, it follows the IBGP behavior for the most part. And then if you're talking about the right, yeah, essentially. Yeah. Yeah, everything else seems to remain the same between regular IBGP and eBGP relationships there. It's just that when we talk about confed eBGP relationships, the big difference is that the next hop doesn't change. And that the AS path is prepended with the confed sub AS sequence. Yeah, in confed eBGP, in either of them, it's not changed. Any questions? Sorry, were you saying something and I interrupted you, or? Okay, cool. Mo, any questions? Alrighty. So that's as much of a theory as I feel that we need to get into. I have a list of things I want to talk about here, but I think I summed them all up pretty well with the demo. So let's go ahead or with theory talk. So let's do a demo here. So what I have is I have a topology here, and actually I'm going to draw this out. I'll just go ahead and make a new layer. So the topology that I have here is that we have 13 routers. We have R13 at the very top, and that's going to be eBGP. So this is going to be in, let's say, AS13. And then we have a real AS, AS100. And then we're going to have these sub-ASs down here that are SAS 65001, sub-AS 65002, and then we have sub-AS 65003. And then we have 4 routers in each of them. So 1, 2, 3, 4, and then we're going to use reflectors to reduce even further the amount of peerings that we need. So actually, whoops, I did numbering wrong. It's going to be 5, 6, 7, 8. So the lower number routers in all of these sub-ASs are going to be the reflectors. So 9, 10, 11, and 12. 9 is the reflector. And then let's say that 5 is also connected to 13. So that's what we're going to do. So keeping that in mind, what we're going to do is we're going to go ahead and configure the first sub-AS here, and then we'll move on to the other ones if time permits. So in terms of sub-ASs, in terms of configurations, we're going to cover that configuration first because it's more logical from the configuration standpoint. So the first thing we need to go into the BGP process. Now, if you'll notice here, this is AS100. This is what I call the real AS number. It's what gets exported out when routes go out of the confederation. So this is going to be the real AS, and it's not a fake AS, but it's an AS number that's only relevant within the Ibtp AS here. Now, what you might think is, okay, well, this is the real AS, so we're going to go rather BGP 100. But actually, and this is what makes confederations kind of hard to switch to, if you're not doing a greenfield deployment, if you're having to change over, this can make it kind of difficult. The process number, the AS number that you use when you configure a BGP process, is the sub-AS number. So instead of going BGP 100 like you might expect, you're going BGP 65001. And then there's a BGP configuration. Now, I'm going to hard code the BGP router ID, just because. And how you configure confederations there is that it's going to be under the BGP confederation hierarchy. And so the identifier is where you put this 100. So the real AS number goes under the confederation identifier, 100. And then you have to configure confederation peers. The reason for this is that this router here has to know what ASs it should be treating as a confederation sub-AS and what ASs are true ASs. Because if you don't configure this, and I configure, let's say, 65,002, this R1 here has no way to know that it should be emulating eBGP, that it should be treating the other AS like it's in the same confederation. So we need to configure these peers, and we need to configure a list of AS numbers for this router to be treating as such. Now, obviously, it doesn't have to do its own AS number because that's just regular eBGP or IBGP. So what we're going to do is we're just going to go ahead and do the other sub-ASs here, which are 65,002 and 65,003. And that's it. And so that's it for the configuration of BGP confederations. There's not much more to it. Besides, BGP, I forget the command here. Actually, no, I'm sorry, that's for route reflectors. I'm talking about this command here, client-to-client reflection. I'll talk about this in a moment, maybe. This, if you want to stop certain clusters from having client-to-client reflection, this is how you do it. But I'll talk about that in a moment. Now, R1's got to be the route reflector. So if you want to configure a cluster ID, you can. And again, this doesn't have to be a valid IP address, whereas if I try to do that with the router ID, it's going to balk and complain at me. So that's just proof of what I said earlier about the cluster ID, but I want to keep the cluster ID the same as the router ID, just for simplicity and for best practice. So that's it. So the next thing we're going to do is we're going to go ahead and configure these routers here, R2, R3, and R4, as route reflector clients. So the way you do that, it's pretty simple. Just for the fun of it, I'm going to do dynamic peers because I'm lazy. But you can do this just with regular static neighbor statements there, but I'm lazy. So I'm going to go ahead and do a BGP listen statement for the range. Allow any range in peer group, or actually RRC for our reflector client. And then I'm going to say neighbor RRC peer group, neighbor RRC, and I'll say remote AS is going to be 65,001. So you're peering using the confederation sub-AS number, not the real AS number. And then As far as everything else goes, you would configure everything else the same way. Update source loopback 0, RC, because I'm peering over loopbacks, and then we're going to be configuring the route reflector client statement. Launch that just so it pushes it into the address family configuration stanza, and that's it. So what we're going to do over here is pretty much the same thing. 65,001, BGP router ID 2222, BGP confederation identifier is 100, BGP confederation peers 65,003. And then we're going to go ahead and configure. Now, the route reflector configuration only requires this route reflector statement here at the bare minimum to get it working. Again, you can configure the cluster ID, you don't have to. So at minimum, in order to configure a route reflector, you only need this. And as far as everything else goes, when you go on these other routers, the client, it's entirely transparent. So these clients are going to do their BGP configuration as if there were no BGP route reflector at all, with the exception that the only peering that they're going to form at minimum is going to be the R1. Now, it can form other peerings, but at minimum, in order to get the topology working, all you're going to need is to form a peering to R1 because that's the route reflector. So I'm going to go ahead and form a peering here. I'm going to call our AS 65,001. I'm going to configure the update source to be loopback 0. And in theory, gotta launch here. And so you can see here that this BGP adjacency change syslog comes up, showing us that we have our BGP peer that's coming up. And so you can see here, it's going to be marking it with the AS number 65,001 there. And so if I go ahead and do a show BGP IPv4 using cast neighbors, you'll see internal link, and that's that. Yep. So it's going to say it's an internal link. Now, if we go ahead and configuration is going to be the same here. So BGP router ID 3323, BGP confederation identifier 100, and BGP confederation peers is 65,002, 65,003. Neighbor 1111, remote AS 111, update source, loopback 0. Got to push this into address IPv4. And I'm just going to go ahead and copy all of this here. Right. Right. Well, what I mean here is it's probably going to be clearer on R1 here. So if you don't do address family IPv4, this route reflecting configuration statement will be out here. So that's what I mean when I say pushing it into address family IPv4. I'm saying that I want the route reflector client statement to be under the address family that it belongs to rather than just out there. It's well, I did it after, but it should be before. You're right, but I did it afterwards, and iOS will automatically convert the configuration from the old standard where you had everything out here to the new standard where you have address family centric configuration. And so if you just type address family IPv4, it will automatically convert the configuration for you. Yep, I'm just doing that as kind of a habitual thing because I've been lobbing BGP recently. Yep, sure. So going back to this, we're just going to go ahead and, whoops, I need to recopy this. BGP router ID 4444. I'm also aware I don't need to be doing this, but it's hard-coded me at this point. So at this point, these guys all should be forming a peering to R1. Whoops, that's not what I meant to do. Show IPBGP summary. And so you can see here we have this BGP peer group here that's listening, and we are forming dynamic peerings. So that's a little extra for you beyond what we're doing in this demo. Now, what I'm going to do is I'm going to configure Loopback One on R2, and I'm going to go ahead and configure, let's say 192.168. actually 192, screw it, 11 dot, can't believe picking a prefix, this is hard. So router BGP 65001, gonna pop into address IMF4 and then network statement this in, 001, mask is 255.255.255.255. We do try BGP, you can see that this is in there. So if I do a show IPBGP 2001, you can see that this is local. And if I go over to BGP on R1, you can see that this is showing up. And if I go over the real test, it's gotta be on the client here. You can see that this is showing up, even though this is not full meshed, right? So we're within this confederation sub AS here. So which means we're still following the split horizon rule, except that because we have route reflectors, we're not really following it. So R2 is advertising that update to R1, and then R1 is going to go ahead and reflect it back to R3 and R4 here. And so on R1, if we do a show IPBGP 2001, you can see here that it's received from an RR client, and so it tells you that. And the origin is IGP and all these path attributes, and you can see here, normally it would say just say internal, not saying confed internal, because being learned to be a confederation peer that's internal to the sub AS there. Now, if we go ahead and go on R3 here, show IPBGP 2001, you can see we have a couple of new things here. It's still confed internal, but you can see here, whereas R2 didn't have the second line and R1 also didn't have the second line, because R3 and R4 got the route by reflection instead of native advertising, it had these two attributes added, which were what I mentioned, originator ID and cluster ID list. So the cluster list has the cluster ID, which is the router ID of the router here by default, which is 1111, so that's the cluster list ID. And then the originator ID is the router that the route reflector received that update from. And so if you learn a route by reflection, you're going to have these two. Now, just if you're curious, what I'm going to do is I'm going to go ahead and apply a debug here. And I'm going to go ahead and this should be enough there. So I'm going to go ahead and shut down the peering. And I'm waiting for the update to reflect. And I'm waiting for a particular debug to come up. So I'm waiting for this router here to send the BGP update containing 2001. It takes a moment after the adjacency comes up. Sure. Nice. Mm-hmm. Well, with confederations, it's you're trying to emulate the IBHP eBHP paradigm within an AS. So it's not any more control plane heavy than usual. The reason that reflectors are control plane heavy is because they're choke points. So when you have a route reflector, the whole point of route reflector is that a client or a client advertises the update to the route reflector reflects it back. Every single client follows that exact same routine. After your update to the route reflector handles it for you, which makes your route reflector at the center of it all. So it's receiving updates from every single client in its cluster. It has to reflect the update to every single client in its cluster. It has to apply those two new path attributes. And so the result is they have a very control plane heavy process. Confederations, that's not a problem because you're not making a choke point out of anything. you're just dividing the ASes up and then reducing the scope of the full measure of the split horizon requirement down to that one sub AS instead of having it span across the entire autonomous system, the real autonomous system. Sure. Yes. So these clients don't see any difference in their behavior. It's the route reflector that has to take on all of the new control plane load. That's right. I didn't see a debug for it. Anyway, what I was expecting to see, and I may try again later, what I was expecting to see is actually, maybe I was doing the wrong debug. Let's try this again. Yeah, I'm not going to spend too much time on it if not, but. Okay, well, we'll keep working here, and then if that comes up, then I will go ahead and look at it. So that's one sub AS that we have working. So if I go ahead and do a show IP BGP, oh, well, I refreshed the peering. Okay, well, I'm sure that'll come back in a moment. All right, in the meantime, though, what we're going to do is we're going to go for the second sub AS here, and then we're going to go for inter sub AS relationships. So what we're going to do is we're going to go ahead and go into config-t. And this is the exact same config there. Oh, okay, there we go. So this is what I was expecting. So this is to prove what I said earlier about how the reflector is going to reflect it back to all clients, including the one that originated it. So you can see there that we sourced an update. We sent an update from 1111, which is our which is their router ID. We're gonna format it with this prefix, this next hop, which is us, where our transport address to R1. Path is local, and the metric is 0. The met is 0. Now, what we're gonna do is we are going to see that we're receiving an update here with an originator of 2222, a cluster list of 1111, and we're going to say, heck no. So this is the debug where we're receiving the reflected route. So we sent a route to R1. R1 is going to reflect it to all clients, including us, on R2. And R2 is going to say, heck no. Denied due to next hop is our own address, and the originator is us. And so this is how it uses the originator ID for loop prevention, because if within the IBGP AS, it happens to loop back around, the originator is us. So it's not going to accept a looped route, right? Now, for these guys, they will accept it because the originator ID is not their router ID. And their, what's it called? And the cluster list is not considered by the client. Remember, the cluster list is only for route reflectors to determine whether there is a loop between route reflectors. The originator ID is what's relevant to the client, not the cluster list. The cluster list just has to be there for the reflection to truly be loop-free between route reflector clusters. So that's as much as I wanted to show you there. Now we're going to go configure the second sub AS, so 65001. Got to figure router ID there of 5555. BGP Confederation identifier is going to be 100. BGP Confederation peers, 65,001, 65,003 peers. Whoops. And then I'm going to... Oh, I configured the wrong AS. Whoops. My bad. No router BGP 65001, router BGP 65002. But now you can see what happens if you try to configure your own AS, and that peering list is not going to let you. So router ID 5555, BGP identifier is 100, and I can actually just copy this. Copy the one without the mistake. So now what we're going to do is, let's say we do change the cluster ID. I'll just show that this works. Let's say we do change the cluster ID from 5555 to 5678. And we're going to go ahead and configure dynamic peers again. We're going to say peer group, and we're going to say RRC, and then neighbor RRC is a peer group. We're going to say that RRC is the Remelia 60002, and we're going to say RRC is sourcing its updates from Loopback 0, and we're going to say that RRC is the router reflector client. Same configuration on these guys. 65,002, BGP router ID 6666, BGP confed identifier is 100, BGP confed peers is 65,001, 65,003, and then same thing here, 5555 from LAS. Gonna go ahead and do this actually. From LAS 65,002, neighbor 5555, update source Loopback 0 and just IP84, and then gonna go ahead and BGP and copy these changes into this guy, BGP router ID 7777. Gonna paste that in, and then router ID, or router SPF. I can't talk today. Router BGP 65002. BGP router ID 8.8.8.8.8. And so that should work. As well as that, oh, well, this is another cluster. As well as that, what I'm going to do is I'm going to very quickly configure this guy to have 5555 as, or 13.13.13.13 as a neighbor. Yeah, that's fine. And then update source x0. Router BGP 13. We're going to say neighbor 5555 remote AS 100. So the difference here is that when we are peering from eBGP into a confederation, we're using the real AS number. We're not using the sub AS number. Remember, the sub AS number has no relevance to anyone on the outside. So we're going to do an eBGP multi-hop here, and then we're going to configure the proper update source. And the moment you should see that this peer comes up, and it does. So you can see here that when we're peering within the confederation, we're using the sub AS number for the remote AS statement. When we're peering outside of it and we're doing eBGP into it, we're using the number that we configured in the confederation identifier statement here in order to peer in. Now what we're going to do is we're going to go to a client here, going to configure a prefix here, and then we're going to advertise it through BGP network 6001 mask 255.255.255.255. And in a moment, you should see that this shows up here. And if we go to R7, you can see that this also shows up here. And if we go ahead and do a show IP BGP 6001, this is confed internal. We have a cluster list of 5678, so this is that custom cluster ID that I set for R5. And then we have the originator of 6666 right here. Now, what we're going to go ahead and do is we're going to go ahead and take this and do a peering between the sub ASs. So what we're going to do is we're going to go ahead and drag a line here between the reflectors. So we're going to go ahead and, actually it might be more fun to do it this way. We're going to do it this way. So we are going to go ahead and take a reflected route on R4, and we're going to push it over to the confederation, over a confederation external peering between R4 and R5 here. That's what we're going to do. So we're going to go ahead and go on R4 here. We will go ahead and go to router BGP 65001. We're going to configure 5 as a peering. So remote AS Now, because this is still within the real AS and we're not out of it yet, like we were with R13, the eBGP peering, we're going to use the sub AS to do our confed eBGP peering. So R5 is in 65,002. So that's what we're doing. 5555 is update source loopback 0. And then we're going to go ahead and do router BGP 65,002. We're going to go neighbor 4444. Remote AS, the others. Sorry. Oh. Yeah. Whoops, forgot about that. So in a moment, unless I boomered something, this should come up. And it does. Okay, thank you for reminding me about the BGP top. So, but that goes to prove a point that, except in some cases, this is real eBGP there between the confederations. So if I do a show IPBGP now, you can see that we have, oh, it's not square brackets, it's parentheses, I'm sorry. So I was saying earlier, square brackets, it's parentheses. I haven't done confederations in a while. So we have this route here, 2001, the one being sourced from R2 here, going over our confed external. The confederation sub-AS sequence here is going to be a parentheses. I believe what I was remembering was the confederation AS. No, the set should be in brackets. I don't know what I was remembering for the square brackets. Yeah, that may actually be a set. I don't remember. Anyway, it could be. I'm not remembering. Anyway, the important part here is that if we do a detailed BGP routing table entry for 2001 in the local rib, we can see here there's a confed external statement here. But you can see the next hop still hasn't changed. So even though this is going over eBGP, quote unquote, like I described earlier, the next hop here doesn't change. So what does change, however, is the AS path, and the AS path gets prepended with lists. Now, just to prove a point, what I'm going to do is I'm going to form another peering, this time off of router 3, and I'm going to try this out real quick. Just to prove a point, I'm going to go ahead and configure 3323 as a neighbor, remote AS 65,001, update source loopback 0, and I'm going to configure 3323 to have a eBGP multi-hop on it. 65,001, neighbor 5555 from LAS, 65,002, 5555, update source loopback 0, and eBGP multi-hop. And then what I'm going to do is I'm going to configure a route map here with, I should configure an IP access list, 1 permit host 2001, and then I'll configure a route map AS prepend. And judging by the name of that route map, you should know what I'm doing. Match IP address 1, and then we're going to set AS path prepend last AS, then we'll prepend it 4 times. And I'm going to go into BGP 65,001 here. We are going to go into address name happy 4, neighbor 5555, and we're going to apply a route map of AS prepend outbound. And then we're going to clear the neighborship outbound. And what you should see is, oh, I don't think AS path prepend works. I might be forgetting something about AS path prepend there. Let's see. Neighbor 5555 policy. Okay, maybe AS prepend doesn't work for confederations. I gotta remember it does. That's okay. What I can do instead, I don't need that. What I can do instead is I'll configure a third sub AS and then we can work with that. So, sorry? No, you were saying? Of hop, yeah, it doesn't matter. Right. Right. That was what I was trying to get to, but I might be forgetting how I probably did forget that AS prepend doesn't work very well. It doesn't work at all with your confederation there, or I may be forgetting something entirely. I don't remember. Anyway, yeah, I haven't worked in federations in a while, but I can show the same point in a moment. I just have to configure the third sub AS, and then I'll be able to demonstrate that point. So the point is though, this reflection works. So what's happening here is when I go into okay, so we're learning this via confed internal, and this is being learned via the reflector. So R5 has a confederation external peering with R4, and that's how it learned 2001 from within this confederation sub AS of 65,001, advertised it out to R5 then reflected that out to its clients within its sub AS of 65,002. Now what we're going to do is, and just for completeness, show it on here. Now what we're going to do is we're going to configure a third sub AS, and then kind of the final demonstration there is going to be showing how the AS path length doesn't matter, and I'll find a way to do that without using AS path prepend. So I always remember the AS path prepend working on the AS sequences there with confederations. Must be remembering wrong. Anyway, we're going to do here is confed identifier 100 BGP confed peer. So this is just the same. This is just the same configuration as before. I don't think I need to do the cluster ID again because I showed how that works. And then BGP listen range 0000/0 peer group. And then we'll configure name peer group, and then neighbor peer group is in remote AS 65,003. Neighbor peer group is in uses base source loopback 0, and neighbor peer group is a route reflector client. And so that should be fine. Oh, and configuration identifier, yep, that looks fine. And then what we're going to do is we're going to go ahead and configure router ID 10.10.10 or 1.10.1. Actually, no, I'm fine using that as router ID. BGP confed identifier is 100. BGP confed peer is 65,001, 65,002. And then we're going to go neighbor 9.9.9.9, 65,003. And it's going to be using an update source, the loopback 0. Now I'm going to go ahead and can copy this and configure this on the other peers. And that should be it for the sub AS there. 65,003 BGP router ID 11.11.11.11. BGP 65,003 BGP router ID 12.12.12.12. We are going to copy that in. And in a moment, this should be forming all of its peerings there. Hi. Alrighty. So now, if I do a show IP BGP here, that's right, because we don't have anything being advertised. Let's advertise something. Int L1 to 10.110.001.255.255.255.255. I'll go into BGP here, launch the address family statement 110.001 mask 255.255.255. And then if we do a show IP BGP on R9, you'll see I'd advertised, just to make a point again, Confederation internal. And then if we go ahead and go right here and we do a detail statement here, cluster list originator confed internal. So the last thing we'll go ahead and do here is configure link from or peering from we'll call it 8 to 9. Why not? So we're going to configure R9, the route reflector here, with a peering statement for 8.8.8.8 remote AS 65,002, 8.8.8.8, this is eBGP, and neighbor 8.8.8.8 update source is loopback 0. Do the exact same thing here. Neighbor 9.9.9.9 remote AS 65,003, neighbor 9.9.9.9 update source loopback 0, and eBGP multi-hop. And you'll see that peering comes up there. So if I go ahead and do a show BGP IPv4 unicast neighbor 9999, you can see that this is external. So even if it's Confederation eBGP, if you do a neighbor show here, it's still an external link because technically there are different ASes, even if it's realistically different sub ASes there. And so I go ahead and do a show IPBGP. You can see here that we have all this right here, right? So this is being learned internally, right? These two prefixes are being learned internally because RA is learning this to prefix from the route reflector and is learning lists are, is learning lists the 6.0.0.1 network from R6 internally from reflection from R6 to R5 back to R8. And then it's learning lists via Confederation eBGP because it's learning it from R9 via the Confederation eBGP peering there. Now I do want to go ahead and show you real quick. If I go ahead and pull up the path selection page, I believe they mention it. If not, I'll just go ahead and mention it. Yep, it does mention it. So if we go ahead and look at step 7 here, which is the prefer eBGP versus iBGP path, you might think there that because it's Confederation eBGP, that Confederation eBGP would be preferred over Confederation iBGP, but nope. There is no distinction in the step between Confederation external and Confederation internal. So not only does the AS path step not care about your Confederation sequence there, but step 7 of the Cisco process, which is preferring eBGP versus the iBGP path, also doesn't care. In the eyes of BGP, only true eBGP is considered eBGP in this context. Confederation iBGP and Confederation eBGP are both squished in with just regular iBGP because technically, realistically, they're part of the same real AS. And it provides the reason here. Paths that contain these attributes in the AS path are local to the Confederation, are local to the real AS, and therefore they're treated as internal paths, regardless of whether they're confed external or confed internal. So thank you, Cisco, for mentioning that for me. So from here, what I can do actually is if I go over to HIPBGP here, there are 2 ASs right here. So what I'm going to do is I'm going to go on RA, and let's see if this works. I'm going to go on RA, and I'm going to configure this exact same prefix, and then push into BGP. So this should be perfectly screwy. 65,003. Actually, I'm going to do before that is I'm going to configure an access list. host 2001, and I'm going to configure actually I don't need to configure a route map. Router BGP 65,002, and I'm going to go ahead and configure it such that oh, hold on a second, I need to do this instead. Access list 2 deny host 2001, access list 2 permit any. Do show IP access list. Yep, that's what I want. All right, so router BGP 65,002, neighbor 5555 distribute list. Oh, I'm sorry, I need to do understandably. Neighbor 5555 distribute list 1 or 2 out, and then neighbor 9999. Actually, I don't need to apply anything there. I'm just gonna advertise this. I'm trying to prevent anything weird from happening. In case you're wondering, I'm trying to prevent anything weird from happening by pushing list route back into the cluster there. So I'm just advertising out to the 9 neighbor. So I do a show IP BGP. Whoops, that is on the EBG here. Right. That's why. I didn't see that coming. Okay, so I need to establish a peering between 7, right? You only have the one that's coming from path. Yep. So I'm gonna go ahead and configure a peering here to 9 from the 65,003, 9999, update source loopback 0, 9999 EBGP, and that should give me the results I want. (65,003) neighbor 7777, remote AS 65,002, neighbor 7777, update source loopback 0, neighbor 7777 EBGP. It's complaining, by the way, because this falls under the peer group there. So anyway, we have this up. So in theory, now we have both halves. Yep. The problem, by the way, in case you are wondering from earlier, is that we weren't getting both paths when I looked on here, because we were only getting the path from R8, because this is only going to advertise one path, is I advertise what I think is the best path. So now if I do a show IP BGP, you can see here that, oh, the problem is the reflector. That's what it is. Problem is the reflector's only going to reflect the best path. That's right. All right. So we go ahead and look at show IP BGP 2001 on the reflector. You can see that it's going to choose the confed external as the best. But if we do a best path reason, which is a command available on iOS XE to see what the best path is, the reason is not because of the AS path. The reason is because of the router ID. So just to prove the point that the path isn't, that these guys are viewed as the same of 0, you can see here that the best path evaluation, the reason for it is because of the higher router ID from the sourcing router here instead of 2222. So best path evaluation, higher router ID, and so therefore it's going to choose the lower router ID as the best because of step whatever number it is after the BGP age. So bit of a rocky demo there. Sorry, go ahead. It selected the one. Oh, I'm sorry, it did. Yeah, it did. Yep. So it did select the one with the intuitively longer AS path. Yep, you're right. Yep. So that's the demo. I don't have too much more to show you. Much more gets into the depths of how this works, which is really more of an IE thing. This is a good introduction for how this works, though. Sorry, Morgan. Yeah, bit rocky because I forgot that AS path prepend doesn't work on the confederation sequences there apparently, and but yeah. If you're wondering why both routes aren't showing up here, by the way, it's because without additional paths, I could configure it to where both paths show up here, but it's not needed. Basically, R12 here is a client of this reflector, and this reflector is only going to reflect the best path. So that's why in both cases I wasn't seeing both paths here. But I will see it here, and that's the important part. So I do think that double peering was needed though, because otherwise R8 would do the same thing. It's also going to only send the best path out here. Yeah. Right. But we can solve that with we can solve that as we did here with a double peering. So that's it for the demo though. Unless you have anything particular I may show you, that's it as far as basic route reflectors and basic confederations go. Any questions from either of you? Sure. I'm recording this, so I'm going to go ahead and push this on YouTube. Actually, I'll stop recording real quick.